Hi everybody. This video will cover section 2 of chapter 3 where we will introduce to you synthetic division. If you want, you can call it polyester division or rayon division, whatever floats your boat. What we're going to do is we're going to present this, and then we're going to show you how you can use this to evaluate functions for a particular value using something called the remainder theorem, so you don't have to compute all those crazy powers. And then we're going to use that tool for testing values to see if they are potential zeros of a polynomial. Okay, so before we do that, we're going to present this thing called a division algorithm, which is kind of weird because it's not really an algorithm, it's more of an existence theorem. And what does it say? Well, it says that if you have two integers a and b with b strictly greater than 0, then there exists unique integers. One is called r, the other one is called q, such that a will be equal to the q times b plus r. And you probably have seen this before. A is our dividend, b is our divisor, the quotient is q, and r is our remainder. And here are a couple of examples. In this case, 61 is a. 7 is q, 8 is b, and our remainder is 5. So we're dividing 61 by b. We have a quotient of q, and our remainder is 5. And that, of course, doesn't make sense because 7 times 8 is 56, plus 5 is 61, and our remainder is within the constraint of being between 0 and b, which is 8. Similarly here, a is 60, b is 8, so our quotient will be negative 8, which will give us negative 64, and then we add 4 to that, which is a remainder, to get negative 60, and once again 4 is between 0 and 8, again in this particular case. So this is more of an existence theorem than it is an algorithm, because typically an algorithm is a procedure you follow to achieve a desired result. Okay, well, it turns out that the division algorithm can be applied to polynomials, just like this. And here we are going to let f and g be polynomials. We are going to make sure that g is less than the degree of g is less than the degree of f, but is still greater than 1, which means there is an x involved somewhere. And if that's the case, then there exist unique polynomials, i.e. there is the only polynomials that will exist for this particular case, where f of x can be decomposed into the product of g and q, and then with an addition of another polynomial called r of x. And the primary constraint, and then the only other additional constraint, is that the degree of r of x must be less than the degree of g, or it must be 0. And once again, f is the dividend, g is the divisor, q is the quotient, and r is the remainder. For a couple of examples, check this out. Here we have f of x. Here is g of x. Here is our quotient. And then here is our remainder. Okay, the division. Here we have our remainder. The degree of our remainder is less than the degree of g of x, so that works out just fine. Once again, we have f, we have g, we have q, and we have r. And this tells us that considering f and g, there's a unique q, and that unique q will be 2xq plus 4. And then there's a unique r, such that g times q plus r will equal f. And then once again, q and r are unique. Now, notice here that once again, we have that the degree of r must be less than the degree of g. Okay, so what if g is nothing more than a first degree polynomial, such as x minus k? Okay, so this right here is g of x. Well, then r has to be of degree less than g of x, which means that r must be a number. And yes, that number can be possibly complex. And this is a special case of the division algorithm. If you divide f of x by g of x, you are going to get some quotient, and then the remainder will be a number. Okay, and that is a special case of the division theorem. And it gets even better. Okay, so if we can express f of x like this, what if you tried to evaluate f at k. Well, if that's the case, maybe make that a k, you are going to replace, everywhere you see an x, you're going to replace that with a k. So that is going to be k minus k, because we replaced the x with a k, times q of k plus r. All right, well, what's k minus k? Well, that bad boy is 0. So this entire thing goes to 0. And we have f of k is equal to r. And that is the remainder theorem. The remainder theorem says that since f of x can be written like this, then f of k is going to be equal to r. Okay? Therefore, if you divide the polynomial by x minus k, the remainder of that division will always be equal to not f of x, but f of k. Okay? And that's pretty easy to prove. We actually proved that in the last slide. And we can use the remainder theorem to evaluate polynomials for a certain value without having to compute all those high powers that actually might be in f of k. Okay, now we want to talk about polynomial division. And I know I have it written out here in slides, but what we're going to do is we are going to walk through this in OneNote. So let's go ahead and do that. Okay, so here we have 3x cubed minus 2x squared minus 150 divided by the quantity x minus 4. And we want to do that division. And how do we normally do that division? Well, we would normally use long division. So what we would have x minus 4, and then over here that would be the divisor, and then our dividend would be 3x cubed minus 2x squared, and then I'm going to add a plus 0x minus 150. And how would we do that? Well, what we're going to do is we're going to multiply x squared minus 4 by something which will give us a by something which will give us a 3x cubed, and that of course would be 3x squared. And of course 3x squared times 3x cubed is, 3x squared times x is 3x cubed. 3x squared times negative 4 is negative 12x squared. And then what we're going to do is subtract, which is equivalent to changing the sign and adding. Actually, let me use another one for that one. Changing the sign and adding, so these will cancel. And over here, we will have positive 10x squared. And then we just continue along. Okay, what do we need to multiply x by to get 10x squared? Of course, that will be positive 10x. And so then 10x times x is 10x squared. And then 10 times negative 4 is negative 40x. And I want to bring down my plus 0x here. Okay, once again, we go ahead and we change the signs and we add. And if we do, these will cancel. And we have positive 40x. We can bring down our 150. And we can do this one more time. Okay, well, we want to multiply x by 40 to get 40x. So plus 40. This will give me 40x minus 160. And then finally, we can once again change the sign and add. So we're going, which is basically subtraction. So we change signs, we add, and we have positive 10. So this right here is our quotient. Well, this right here. And our remainder is 10. Now, the idea behind synthetic division is by trying to remove the things that we don't use to do the computation. And one thing that you'll notice that we didn't use, we really didn't use the x's. Instead, we used the place of the terms in the division, where they physically lie in the division. Or we could say that the location of these terms is redundant, and the value of and the exponent associated with the variables are basically redundant. As a consequence, we could rewrite this without the x's. So let's go ahead and do that. Okay, we will have -4, 3, -2, 0, -150. All right, and then we would have 3, -12, a line, 10, 0, 10, -40, another line, 40, -150, -40, no, positive 40, -160, 160, and then another line, and then we would have positive 10. Notice we still have divisions. We can actually still get the -4 by -12 by multiplying the -4 by 3, and also the -40 by multiplying the -4 by 10, and so forth. Now also notice that we have a 3 here and a 3 here. We really don't need this 3. We have a 10 here and a 10 here. We don't really need this 10. We have a 0 here and a 0 there. That's kind of redundant. We don't need that. We have a 40 here and a 40 here. That's not necessary. We have a 150 here and a 150 there. That's not necessary. But I probably should still include the 3, the 10, and the 40 up here. Okay, without the x's. Okay, so we can actually go ahead and consolidate all that stuff, and if we do, I actually want to keep that there, so I'm going to lasso all this and make it go away. And if we do, what I can do is rewrite this as -4, 3, -2, 0, -150, and then I'm going to have a -12. I still have my line, my 10. I will have a -40 right here, another 40 here, another line. I will have a -160, and then I will have a 10. Okay, now kind of notice what I can do then. I can actually take these two terms without losing any information. I could take these two terms or numbers and move them up. I can take these and move them up. And if I do, I will have something that looks like this. -4 over here. Oh, let's not forget my 3, 10, and 150, and 40 over here. 3, 10, and 40. I will have -4. I will still have my 3, -2, 0, -150. I will have my -12 down here. I'm going to move my -40 up. All right, and then I'm going to move my -160 up. Okay, I'm going to draw my line. Now I need to scroll down. I'm going to have underneath the 12 my positive 10, my 40, and then my other positive 10. Okay, and of course up here I still have 3, 10, and 40. Okay, now the other thing I can do is I can take this 3 and I can rewrite this 3 down here, just for kicks. Let me just do that in another color just to show that. So all I'm doing is rewriting the 3. Now does this work? Does this kind of make sense? Well, check this out. -4 times 3 gives me -12. If I do 2 minus 12, I get 10. -4 times 10 is -40. 0 minus -40 is 40. -4 times 40 is -160. 150 minus 160 is 10. Okay, and also notice that this right here, the 3, 10, and 40 is basically nothing more than a repetition of this, of the 3, 10, and 40 up here. So I don't really need this. Okay, there's one more thing that I want to do. Okay, notice here that I'm doing subtraction. What I can do instead of subtraction is just change the sign and add. So let's go ahead and do that. I'm going to let me change my colors here. I want to be color coordinated. let me change. I'm going to have my 3, -2, 0, -150. So instead of -12, I want to have a +12 here. And then when I add that, I will get 10. I still want my 3 here. Instead of -40, I'm going to have +40. And instead of, and when I add those together, I'll get 40, which I'm looking for. Instead of -160, I'm going to have +160. Well, I don't need the positive there. 160. And that, of course, will give me 10. And to compensate for that, instead of having the -4 in the x minus 4, I'm going to include the opposite of that, which will be 4. And the algorithm still, and the synthetic division still works. 4 times 3 is 12. 12, -2 plus 12 is 10. 4 times 10 is 40. 0 plus 40 is 40. 4 times 40 is 160. -160. 150 plus 160 is 10. Now this right here are the coefficients associated with the quotient. And this right here is the remainder. So this is going to be equal to 3x squared plus 10x plus 40. And our remainder is going to be 10. And if you were going to write that in the appropriate form, this would be 10 divided by x minus 4. So we have that 3x cubed minus 2x squared minus 150 divided by x minus 4 is actually equal to this. This is our quotient, and then this would be our remainder. Okay, and if we actually multiplied everything by x minus 4, we would have 3x cubed minus 2x squared minus 150 is equal to 3x squared plus 10x plus 40, all that times x minus 4, our divisor, so this is our quotient, I actually did that backwards, and plus 10, which would be our remainder. Okay, so this is our divisor, this is our quotient. And this right here is what we call synthetic division. It only works when you are dividing your polynomial by x minus k. And then the way you set that up is you put in, and the way you would set that up is that in your form, you put k here, you put the coefficients of your polynomial here, okay, and then it is basically addition. Now, to get comfortable with this, we actually need to do a couple of examples. And here is our first example. So we want to use synthetic division to compute 5x cubed minus 6x squared minus 28x minus 2. So let's go ahead and do that. All right, now, once again, we are going to set up our coefficients. Here we're going to have 5 for x cubed, -6 for x squared, -28 for x, and then -2 for our constant term. Okay, since we're doing x plus 2, we want to, instead of having a plus 2 here, we're going to want the opposite of that, which is -2. Okay, then we want to draw a line down here, and I'm going to repeat my 5. Okay, and here we go. -2 times 5 is -10, so I'm going to put -10 here. -6 plus -10 is -16. Okay, -2 times -6 is +32. -28 plus 32 is 4. Then finally, -2 times 4 is -8. -2 plus -8 is -10. So this right here is our remainder. And our quotient is going to be 5x squared minus 16x plus 4. Okay? Therefore, this is going to be equal to, well, once again, 5x squared minus 16x plus 4 plus, no, not plus, let me fix that. Because it's a negative 10, so it's going to be minus 10 divided by the divisor, which is x plus 2. Okay, so this is actually how you would write the answer into MML. The only difference is if they ask you to express it in the form of f of x is equal to x plus 2 times q of x plus r of x, or plus r, not r of x, then you would write this as x plus 2 times 5x squared minus 16x plus 4 minus 10, which is what you would do if you multiply this entire equation by the quantity x plus 2. Okay, let's move on. Okay, we talked about the remainder theorem before, right? The remainder theorem basically says that if you want to evaluate a polynomial by k at the value k, then you want to divide it by x minus k, and then the remainder, whatever that is going to be equal to f of k. So we found from our previous example that the remainder of 5x that the remainder of 5x cubed minus 6x squared minus 28x minus 2 when divided by x plus 2 is equal to, has a remainder of negative 10. As a consequence, it turns out that if you evaluate f at negative 2, the answer is going to be negative 10. And if you don't believe me, what you could do is you could actually basically evaluate f of negative 2 by computing it directly. And if you did, you can come through this calculation, you'll get the exact same thing, negative 10. But here you can do it without having to compute the powers, which in this particular case is not that bad because we're just it's a small number to small powers, so it's pretty easy to compute. But if you had larger numbers and you were dealing with a 7th or 8th degree polynomial, doing it directly may be a daunting task. Okay, so let's use the remainder theorem to evaluate this polynomial when k is equal to negative 3. So what we want to do is we want to divide this by x minus k, which in this case will be x, which is going to be x minus negative 3 or x plus 3, and see what the remainder is. Okay, well, to set this up, we will first put in our coefficients, which will be a 1, a 0 for the x cubed term, since there's an applied 0 there, a 3 for x squared, a negative 4 for x, and then a negative 5 for our constant term. Okay, since we're dividing it by x, since we're divided by x plus 3, we want to put in the negative of 3, which is, well, minus 3, which ironically is what k is to begin with. Okay, and then we want to draw a line down here. We want to bring down the 1. Okay, so we have negative 3 times 1, which is negative 3. 0 plus negative 3 is, well, negative 3. Negative 3 times negative 3 is positive 9. 3 plus 9 is 12. Negative 3 times 12 is negative 36. This adds to negative 40. Negative 3 times negative 40 is positive 120. Negative 5 plus 120 is 115. And this is our remainder. Remember, this is the remainder. So it turns out in this particular case that if you evaluated f at negative 3, your answer will be 115. Don't believe me? Go ahead, knock out your calculator and see what you get. So since this is a great approach for figuring out, for evaluating f of k using the remainder theorem, it's basically whatever the remainder theorem is, we can actually use this approach to figure out what values of k, what values, and okay, let's call it k again, is equal to 0. And those are, and if we have a case such that f of k is equal to 0, it turns out that k is a 0 of the function, which is what we want to talk about here. The 0 of any polynomial is that number, k, such that f evaluated that number is equal to 0. And those zeros are also the x-intercepts of the graph of the function. Or I should say that the zeros are the x values of the x-intercepts of the graph of the function. What is the y value? Of course, it is 0. And it also turns out that the 0 is that a 0 of the function f is also a root of f, and of course is also a solution of the equation when f of x is equal to 0. Okay, so how do we determine it? Well, how do we determine if a given number, in this case alpha, is a 0? Well, we use synthetic division to find out what f is when evaluated at alpha, and if it turns out to be 0, it's 0. If it doesn't, then it's not. That's simple. Okay, so let's actually do an example let's do an example to highlight this. And here we are going to let f be equal to x cubed minus 4x squared plus 9 minus 6. And we want to see if k equals to 1, if 1 is 0. So we can go ahead and set this up using synthetic division. Of course, it'd be really easy just to plug in 1 and see what you get. But we're not going to do it that way. We're going to do it this way. And then you can validate it using the latter approach. So let's set up our synthetic division. We are going to have the coefficient of x cubed is 1. The coefficient next to x squared is negative 4. For the linear term, we have 9, and then we have negative 6. And since we are evaluating this k equals to 1, we just want a 1 here. Okay, and here we go. First thing we want to do is bring the first one down. First one down. That sounds kind of weird. Okay, and then what's 1 times 1? You guessed it, it's 1. Negative 4 plus 1 is negative 3. Negative 3 times 1 is negative 3. I love these hard multiplication problems. 9 minus 3 is 6. Negative 1 times 6 is 6. 6 minus 6 is 0. This is the remainder. The remainder is 0. That implies that f evaluated at 1 is equal to 0, and 1 is indeed a 0 of f. Okay, let's do one more example. Uh-oh, this one has a complex number. That's not fair. Well, nonetheless, we can still use the exact same approach using complex numbers. Okay, so let's go ahead and set this up. The coefficients of my dividend, we have for the quartic term, we have a 1. For the cubic term, we have a negative 2. Actually, I'm going to need a lot more space. I have a negative 2 for my quadratic term. I have a 4 for my linear term. I have a 2, and then for my constant term, I have a negative 5. Well, of course, now I'm going to divide. Since k is equal to negative 1 is equal to 1 plus 2i, I can just write 1 plus 2i here. Okay, make space for my second line, for my second row of numbers, draw a line, and bring my 1 down. Now, 1 plus 2i is, well, that's easy. That's just 1 plus 2i. 2 minus 1 plus 2i is negative 1 plus 2i. Okay, now I need to multiply 1 plus 2i times negative 1 plus 2i. So let me do that over here. That will be 1 plus 2i times negative 1 plus 2i. Now I can factor out that negative 1, and if I do, I will have negative 1 plus 2i. And I'm taking the negative from here, so the negative of negative 1 is 1. The negative of positive 2i is minus 2i. Now look at this. This is a complex conjugate pair. So this is going to be equal to the square of the real part plus the square of the absolute value of the imaginary part. And the imaginary part is 2, or the absolute value of the imaginary part is 2. And so the square of that is 4, so it's going to be 1 plus 4, which will give us negative 5. So we are going to have a negative 5 here. And then 4 minus 5 is negative 1. And then negative 1 times 1 plus 2i is going to be negative 1 minus 2i. And then we're going to have 2 plus negative 1 minus 2i, which is going to be 1 plus 2i. And then we are going to have, and then we need to have 1 plus 2i. I'm sorry, this is a 1 minus 2i, my mistake. 1 minus 2i. And then we have 1 plus 2i times 1 minus 2i. Well, we actually have that right here. And that is going to be the square root of the real part, or the square of the real part, which is 1, times the square of the absolute value of the imaginary part, which is 2. 2 squared is 4, and that will give us positive 5. So when we multiply these two together, we will get positive 5, and then negative 5 plus positive 5 is equal to 0. So it turns out that f of 1 plus 2i is equal to 0, and this is also a 0 of f. Okay, I have a couple other problems just to walk through. This is a synthetic division problem, and this one has fractions. Man, doesn't get any worse, does it? Okay, so here you're dividing all this by x minus 1/3. Okay, so to set this up, we have to set up, so once again we need to set up our synthetic division thing. Here the coefficient for the cubic term is 1/3. The coefficient for the quadratic term is negative 8 over 9. The coefficient for the linear term is 8 over 27. And then the coefficient for the constant term is negative 1 over 8. Since we're doing x minus 1/3, well, I want to have a positive 1/3 here. Remember the opposite of this particular value here. Okay, so I can draw my line here, bring down the 1/3, and the first thing I want to do is do 1/3 times 1/3, which is 1/9. Negative 8 over 1/9 will be negative 7/9. Negative 7/9. Okay, negative 7/9 times 1/3 is negative 7 over 27. All right, well, 8 over 27 minus 7 over 27 is 1 over 27. I forgot the 81 here. It's kind of important, especially now. And then 1/3 times 1/27 is, you guessed it, 1 over 81. And this will be equal to 0. So it turns out that when you divide this, the result is going to be 1/3 x squared minus 7/9 x plus 1 over 27, and it divides evenly. There is no remainder. And then finally, we have this particular form. We want to express f of x in the form of x minus k times qx plus r for the case where k is equal to negative 1. So what we need to do is we need to divide this by x minus k, which in this case will be x plus 1. X minus negative 1 is just like x plus 1. So let's go ahead and set up our synthetic division. We have 3 here for the cube term, 1 for the quadratic, 1 for the linear, minus 7 for the constant term. And of course we want to have a negative 1 here. There, or just realize it's the opposite of that. Okay, draw our line, bring our 3 down. Negative 1 times 3 is negative 3. 1 minus 3 is going to be negative 2. Negative 1 times negative 2 is 2. 2 plus 1 is 3. Negative 1 times negative 3 is negative 3. Negative 7 plus negative 3 is 10. So this is our quotient, and this corresponds to 3x squared minus 2x plus 3. And this is our remainder r. And therefore we can write this polynomial as follows. X plus 1, cause it's x minus k in case negative 1, times 3x squared minus 2x plus 3 minus 10. And that, of course, will be equal to this term right down here. Now, and that is pretty much all that I have. I just want to remind you that synthetic division only works when you are dividing a polynomial, whatever that polynomial is, by x minus some number. Okay? And that is equivalent to evaluating that polynomial at the number k. Now, if it turns out that this term number ends up being 0, then that value k happens to be a root, or a root, or indeed a 0 of the polynomial. And finding roots and zeros, and this is one technique for finding roots and zeros of a polynomial. And in section 3, we will talk about other ones. And if you have any questions, with that I am done. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.